Hello guys, welcome to Yebo Physics on a Wednesday afternoon. I hope I find you well. And in today's tutorial, we intend to look at problems that involve lenses. Okay, so that is going to be the focus of today's tutorial. That is lenses. I'm just experiencing a bit of some feedback here. Let's see if we can fix this. All right, this should be fine. So I'm already showing a question, question 35. Like I indicated, it's going to be mostly questions that involve lenses. And I hope you are keeping up with your revision as you are preparing for the upcoming exams. And I hope that the tutorial sessions are helping, and I hope they have been helping. So let's get on and start with the problem solving. So we just have got a few problems, so I don't think this session is going to be a lengthy one. The first question reads, the object in a ray diagram is perpendicular to the principal axis, but does not have one end lying on the principal axis. The minimum number of rays that must be drawn in this ray diagram in order to determine the position of the image is. Okay, so such a question is, you must remember the rules of ray diagrams. Okay, you should recall that's question. Rules of ray diagrams. Okay, so this is our principal axis, and this is going to be your lens. Okay, convex lens per se, and this is going to be your focal point to F and to F. And we're told that we have got an object that is perpendicular to the principal axis. Okay, and one of the sides is not on the principal axis. So the first ray that you should recall is that any ray that passes through the center of the lens passes through unrefracted. Okay, so if you have got your ray that will pass through the center of the optical length of the optical lens, it will pass through unrefracted. Okay, so I'll say this is rule number 1. Then for a ray that is parallel to the principal axis, when it reaches the lens, it will bend and pass through the focal point. Okay, like that. So my rays are not straight because it's freehand. Okay, so it should pass through the focal point. So I'm just going to do this. So assuming that's where our focal point is. Okay, so this will be your second rule. Okay, and then the third one is the ray that passes through the focal point before reaching the lens. When it reaches the lens, it will be refracted and move parallel to the principal axis. Okay, so that is your number 3. So these are our rules for a ray diagram. Okay, and at this point where these rays converge, that is where your image will be formed. Okay, so if this is accurate, this should be beyond 2F. This is where your image will be formed. And this is your object. So for an object placed between F and 2F, it will be formed beyond 2F. Okay. So that is so these are the rules that you should remember for your ray diagram. So we need 3 rays to accurately position our image or locate our image. So that was the first question. Question 36. And the question reads, if you stand closer to a concave mirror, I'll read that again. If you stand closer to a concave mirror than a distance of 1 focal length, the image you see is, so the image, okay, object located between F and the mirror. So for an object formed object distance less than F, okay, if object distance P is less than the focal length, which means image is virtual and upright. You can confirm this in your notes. Okay, so it's a virtual, it's upright, and it's also enlarged if you are to add all the attributes of that image. So it's enlarged. Okay, and this is true also for, this is true also for a convex lens. So this is also true for a convex lens. That is for an object placed between the focal length and the optical center of a convex lens or a converging lens, you will form a virtual, upright, enlarged image. Okay, so these characteristics you should know. Okay, so if you refer to these diagrams from your notes or from the sketches, or you can try also sketching these ray diagrams, you would satisfy yourself that indeed for an object placed between F and this and the mirror, you form a virtual image which is upright and enlarged. Upright, virtual, and enlarged, or magnified if you like. So we can check that. So that was question 36. Let's look at question 37. So question 37, what does it say? Of the possible statements that parallel rays are brought to focus by 1, a concave mirror, 2, convex mirror, 3, converging lens, and 4, a diverging lens. Okay, so if we are to look at the terms in terms of lenses, to bring parallel rays to focus, you need to converge the rays. Okay, so to bring parallel rays to focus, you need to converge the rays. Okay, and therefore from there, which means we need a converging lens. Okay, we need a converging lens. But which type of mirror do we need? Which type of mirror do we need? So if we look at our mirrors, you have got a convex lens, which looks more like this. Okay, this is your convex lens. Okay, so if you have got rays parallel to the principal axis, when they reach the convex, okay, so this is not a lens, this is a mirror, sorry, convex mirror. So when this ray parallel to the principal axis, when it reaches the mirror, it will be reflected in such a way that it will pass through your focal point. The virtual ray will pass through the focal point. Okay, that's not a straight line, so let's try again. Trying to draw a virtual ray. Okay, so which means that a convex mirror will diverge. It will not converge the rays, it will diverge the rays. Okay, and let's see what about a concave lens. So this is not a concave lens, a concave mirror. All right, so for a concave mirror, if you've got a ray parallel to the principal axis, there you are. When it reaches the mirror, it's a reflecting surface, it will be reflected. Okay, passes through that point. Also similar, if you've got parallel rays on the other side, they'll be reflected, pass through the focus point. Okay, so which means that a concave mirror will converge the rays. So which means in terms of mirrors, we need a concave mirror. So we need a concave mirror to converge rays. So we need a concave mirror. So which means that in that case, the options that we'll take, it's option 1, concave mirror, and converging lens. So that's 1 and 3. Okay, and also if you look what we said earlier on question 36, all right, for an object placed between so the concave mirror is almost similar to a converging lens, right, in terms of the objects, the images that are formed by objects, right? So there are some similarities that you pick up there. So our option, we say that will be 1 and 3. So we can check that. Now move on to question 38. Question 38 reads, Ilona and Olivia observe a visual image formed by an object placed at distance f/2 in front of a convex lens of focal length f. They argue about where to place a concave lens of focal length -f to have a visual image at the same location relative to the lens that they had with a convex lens. Ilona says the object should also be placed at a distance f/2 in front of the concave lens. Olivia says this won't work. Which one, if either, is correct and why? Okay. So these the two people referred here, they're having an argument. But first and foremost, what they've done, they've placed an object f/2 in front of a convex lens. So which means if we were to draw a situation for the convex, object distance p is equals to f/2. Okay, the focal length is f, it's positive f, that's the focal length. And remember what we discussed in question 36, an object placed in between the focal length and the optical center of the lens will form a visual and upright image on the other side, right? So which means that the image formed here is virtual image is virtual upright, and it's on the other side of the lens, on the other side of lens. Okay, it's formed on the other side of the lens. So these are the characteristics of the image that is formed by the scenario that we have here. Okay, so this is what they did the first time. Now the argument is now they have a concave lens. So a concave lens and they're arguing if we would put the object at f/2, is it going to work or not? Okay, so who says f/2? Ilona says the object should be placed. Ilona says p should be equals to f/2. Olivia says p will not be equal to f/2. That's Olivia's. Olivia says this won't work, right? Okay, so now we can use our equation. Our equation for Rayleigh's positive, right? You remember the equation, the lens equation, right? And we consider the convex lens, right? We consider the convex lens, calculate and see, or compute and see where the object should be, where the image will be formed. Okay, so consider and use 1/f equals to 1/p plus 1/q. All right, substitute, that's 1 over f. This is going to be f over 2 plus 1 over q. And this will be 1 over f equals to 2 over f plus 1 over q. Okay. If you are to make 1 over q the subject, it's going to be 1 over f minus 2 over f. Therefore, if you compute your q, it's going to be equals to negative f. So like we said, it's going to be on the other side, all right? On the other side, because q is negative, all right? So this is the case for the convex lens, okay? Now, Ilona is arguing that for the concave lens, let's place the object at the same distance, which is f over 2. If this is true, then if we calculate for q, we should be able to get, negative f, okay? If that is true. So if true, I'll just comment, if true, q should be equals to negative f if Ilona is true, okay? But if you don't get a negative f, then it means that it's not true. And that means that Olivia is right, that it will not work. So let's consider the concave lens where your f is, focal length is negative, okay? So it's going to be 1 over negative f equals to 1 over p plus 1 over q, okay? So this becomes negative 1 over f equals to 1 over p plus 1 over negative f, okay? So we've substituted, because they're saying, Ilona is arguing that we want to maintain the same position. Therefore, if we're maintaining the same position, the image should be formed at the same position, right? Right. So from there on, if we simplify and put 1 over p the subject, 1 over p will be equals negative 1 over f plus 1 over f, okay? So which means that 1 over p is equal to 0, okay? And therefore, this implies that p is equal to infinity, right? That's the implication, right? P will be equal to infinity, right? So we can see that from this calculation, it implies that if the object is placed at f over 2, it will not work, okay? Because the value of p that we're getting, it's not equal to f over 2, okay? So which means that this is not true. Which means Olivia is correct, which means we cannot place the object at f over 2. So from the calculation that we've made there, which means p would be equal to infinity, right? I hope you get the hang of it. Question 39. Question 39 reads, a convex lens were made of very thin clear plastic filled with air and were then placed underwater where n is equals to 1.33 and where the lens would have an effective refractive index of equal to 1. The lens would act the same way as, okay, so here we should understand our lenses. So for a convex, so we should understand their architecture, okay? So the convex lens, for it to be able to converge rays to a focus, it has a higher refractive index than the medium. Okay, higher refractive index than the medium. So the n of the lens is greater than the refractive index of the medium. So to summarize that, n of the lens is greater than n of the medium. Okay, and then how about the convex? Concave rather, concave. So it's the opposite, okay? It actually has a lower refractive index than the medium. All right, for it to act as a concave lens. So now what does the question say? So we have a convex lens, all right, made of very thin plastic. So it's filled with air, okay? So it's filled with air. Air has got a refractive index of 1. And because the plastic is very thin, it's being assumed that its contribution is going to be negligible, okay? So, which means that the refractive index of the lens, n of the lens is equals to 1.00, just 1.0, okay? Then n for the medium, because it's in water, that's 1.33. Therefore, we realize that the refractive index of the lens is less than the refractive index of the medium. Okay, and if you look at this relationship, it means that it matches with the definition of that of a convex lens, all right, of a concave lens, which means that this convex lens, when placed in water, would act as the same way as a concave lens in air. Okay, concave lens in air. So I hope you would recall the architecture of the convex lens and the concave lens so that you know the difference. Question 40 reads, a telescope is constructed with two lenses separated by a distance of 25 centimeters. The focal length of the objective lens is 20 centimeters. The focal length of the eyepiece is 5 centimeters. Calculate the magnitude of the angular magnification. Okay, so we are looking for angular magnification. So it's equals to focal length of the objective lens over the focal length of the eyepiece. Okay. Focal length of the objective is 20 centimeters over the focal length of the eyepiece, which is 5 centimeters. Because it's magnification, then there are no units. So that's 4. So remember your equation. It's your focal length of the objective lens over the focal length of the eyepiece. And that way you do that simple computation. Question 41 reads, which ray diagrams are correct? The 3 rays in each diagram are distinguished by different types of lines. Hint, check the behavior of each ray as it interacts with the lens. Okay, so remember, a lens will always refract rays, only except when the light ray is passing through the optical center. So if you look at the first image already, A, you've got a line that is passing straight through, unrefracted, but not at the center of the lens. So already that one is out. We expect a straight through line only when a ray of light is passing through at the optical center. So that dotted line there is incorrect. Okay, this path is incorrect. Also, we dismiss B for the same reasons. Okay, we don't expect that. Then any ray that passes through the principal axis will pass through unrefracted. So that is okay. Any ray that passes through the optical center will pass through unrefracted. Any ray parallel to the principal axis will bend and pass through the focal point. So which means we can take option C. And again, we have the same scenario, only that we have a ray that passes through the focal length before reaching the lens and will be refracted when it reaches the lens so that it moves parallel to the principal axis. So all the rays on D are correct. Okay. Then C, we've got your ray that passes through the optical center, and we've got our rays that pass through at the bottom of the object, right to the apex of the image. It's converged, and we have the same ray also, which is following a similar path. So all these are correct: C, D, and E. Question 42, which will be our last question for today. When you stand in front of a convex mirror, the image you see is, so remember, convex mirror, okay, will always cause rays to diverge, right? Always cause rays to diverge, and they converge on the other side, and virtual rays converge on the other side, okay? Therefore, it is the virtual rays which form a virtual image, or the image. So it's always virtual and upright, because it's formed on the other side. Virtual and upright. So this is it that I had for you guys this afternoon, just to take you through the revision and practice of question that involve lenses. Okay, so I hope that you go through practice questions that involve lenses, practice questions that involve mirrors, know how to use your Rayleigh's positive equation. There'll be also more problems to look at in the next coming tutorial. So from me and everyone else in the studio, it's a goodbye. I wish you all the best as you are preparing for your final exams.